In the last several videos, I've commented on multiple occasions that we needed to use spectroscopic evidence to back up our theoretical predictions of what molecular orbitals would look like and what their energy levels would look like. We're going to talk about two main techniques to do that in this course. We're going to talk about infrared spectroscopy and photoelectron spectroscopy. Both of those techniques rely on the fact that the shape of the potential energy curve for a bond changes as the amount of electron density between those nuclei changes. So the electron configuration of the molecule changes the potential energy curve. If you were to excite an electron from a bonding molecular orbital up into an antibonding molecular orbital, you would lower the bond order. And that would lengthen the bond, weaken the bond, change the shape of that potential energy curve. So what you're seeing in the diagrams below are two potential energy curves. One of them has a shallow well and one of them has a sharp well. So stop and think for a moment, pause the video if you have to. Which of those two diagrams should correspond to a more rigid bond, a bond in which the two nuclei are held more tightly together? Well, if you chose this one, then you are correct. What we see in that potential energy curve is we see that it's a very sharp well here. It's a very deep hole, so to speak. And there are quite large energy gaps here between the different vibrational energy levels. So what that means is that to go from having your molecule vibrating a little bit up to a higher vibrational energy level where the atoms are vibrating a bit more away from each other requires the input of a significant amount of energy. So if you were to think about something like a really stiff spring, for example, we have to push quite hard to make it bounce. That would correspond to the diagram on the right with that sharp energy well and big difference in energy between the vibrational energy levels. The diagram on the left, on the other hand, has a much shallower well. It also has a longer average bond length, but more importantly, the shape of this well here is really sort of shallow and spread out, and the gap between the vibrational levels is much smaller. So now we can think of a really springy spring where you don't have to apply that much energy either as a pull or a push to get it to vibrate easily. It's important that we remember that molecules are always in motion. Vibrational spectroscopy, which is what infrared spectroscopy is, wouldn't work if molecules weren't constantly in motion. So at this point, I'm going to switch apps so that I can show you what these vibrations actually look like. We're going to look at one molecule that is not very rigid and one molecule that is much more rigid, and hopefully you can see the actual difference between how these vibrations look. So what you're seeing now is a program called CHEM. This is a piece of computational software which we can use to calculate atomic orbitals, energy level diagrams if we just put one atom in, but that wouldn't be very interesting. Molecular orbital energy level diagrams, which we can do here. I simply would have to set up my calculation, which I do like so, and then get it to do the calculation for me. Ask for my geometry optimization. It does the calculation. I had my geometry pre-optimized. And then I can look at the orbitals. And this generates for me a nice molecular orbital energy level diagram for a molecule that in this case happens to be a bromine atom and an iodine atom, because that's a nice, simple diatomic system. I needed a heteronuclear diatomic for reasons we'll discuss later. And And I could show you all the pictures of the different molecular orbitals, but we're here today to look at the vibrations. So I'm now going to compute vibrational analysis. And once it's done that, it will pull up the vibrational spectrum for this molecule, which, because it's a diatomic, isn't the world's most interesting thing. There's one vibration that can happen. And if I choose to animate the vibrations, you can now see these atoms pulling apart from each other and squishing back together, vibrating in real time. So now I'm going to stop that, and I'm going to switch over now to building a smaller, more rigid molecule. So now I have built lithium hydride. Going to do the same thing, set up my calculation. I've pre-chosen all my options so that you don't have to sit through that part. Compute my vibrations. And now if we animate those vibrations, you can see that this bond looks a lot less bouncy, so to speak, than the molecule with the bromine and the iodine did. That's because this is a shorter, more rigid bond. You can see the hydrogen on the right looks like it's moving more than the lithium on the left. That's a function of the fact that they have different masses. But I had to choose heteronuclear diatomics in order to display this principle. So now that you've seen what those vibrations look like and how they change with the rigidity of the molecule, the bromine iodine molecule versus the lithium hydride molecule. The one with the bigger atoms, the longer bond, the less rigid bond, had a much bouncier vibration, and it requires less energy to excite that molecule into a higher vibrational energy level compared to the lithium hydrogen bond, which is much shorter and much more rigid. And generally speaking, when we're using infrared spectroscopy to analyze molecules, that's the sort of thing that we're looking for. We're looking for a comparison of rigidity of the bond. And so, for example, we can very easily tell the difference between a carbon-oxygen double bond versus a carbon-oxygen single bond, because the double bond is stronger, more rigid, and requires more energy to excite the molecule into a higher vibrational level. This is what the infrared spectrum for a molecule might look like. This happens to be a common alcohol because I'm an organic chemist and that's what I use my IR for. What this infrared spectrum tells me is that I have a big, ginormous peak over here that is broad and fat, and that corresponds to an OH bond. If I had had any carbonyl groups, C double bond O in my molecule, they would have been around about here. There aren't any. And there are representative signals for lots of other functional groups too. My alkynes would tend to be down around 2200. My alkenes, on the other hand, are down around 1600. These guys little here, the pointy ones, as opposed to the big broad one, that's a CH stretch. And you can see you get a very potentially complicated pattern. This section over here on the right is actually called the fingerprint region. It's different for every molecule. It's usually quite a complicated region, and we can in fact use it essentially as a fingerprint for the molecule. If you make something and you're not sure which of 6 things it is, you could compare that fingerprint region of the IR to all of their fingerprints and identify it that way. The reason that I had to use heteronuclear diatomics in that modeling software to show you these vibrations was because the modeling software was predicting an IR infrared spectrum. And it turns out that a molecule will only be what we call IR active. It will only show up in an infrared spectroscopy experiment if increasing the vibrational energy level changes the net dipole of the molecule. So for those diatomics, raising the energy level, making them vibrate more, changed the average bond length. And by changing the average bond length, I changed the size of the dipole moment. And so it is therefore possible to see those molecules in an infrared spectrum. Once we get past the diatomics, the vast majority of molecules have some sort of vibrational mode that will change the net dipole of the molecule. Even if you have a molecule that's overall neutral that has no net dipole, if vibrating the atoms in a certain way gives it a temporary dipole, then you could still see it on the infrared. But you won't see a signal for every single possible vibration. You will only see a signal for the ones that change the dipole of the molecule as a whole. If we were so inclined, we could choose to predict the number of normal modes that a molecule might undergo. So for a larger molecule, we would stop and say, well, there are a certain number of atoms. We'll say there's n atoms in this molecule, and each of them could move in a direction that had a component along the x-axis. It could move in a direction that had a component along the y-axis, and it could move in a direction that had a component along the z-axis. So basically, there's 3 different directions it could move in, and then that'll be 3 different directions for every atom in the molecule. So then that gives you a total of 3n modes or motions that the molecule could possibly have. But if every atom just moves along the x-axis, that's not a vibrational mode. That's the molecule moving along the x-axis. That's translational motion. Same with the y, same with the z. So we have to subtract 3 off of our total set of options. And then we also have to remove some options that correspond to rotations, because this form of spectroscopy looks at vibration, not rotation. And so we wind up with linear molecules having 3 times the number of atoms minus 5 possible vibrational modes, and nonlinear ones having 1 less. What do those modes look like? I mean, the diatomic was easy. You just imagine them bouncing back and forth. These are different types of normal modes that you might see for larger molecules. We have the symmetric stretch. We have the asymmetric stretch. We have the scissor, the rock, the wag, the twist. And here is your molecule vibrating in all sorts of possible crazy different ways. Don't memorize those terms. I don't want you to. I don't need you to. I included them so that you could kind of see the relationship between the movements. And I apologize if this diagram interactive little thing is giving anyone a headache. Let's move on. So knowing that a molecule is only going to show up in the infrared if stretching it changes the dipole, which molecules would we expect to be able to show up on an infrared spectrum? Well, we should be able to rule out argon right away because it's not a molecule. It's only got 1 atom. 1 atom can't vibrate. There's nothing to vibrate against. Looking at the others, N2 is a homonuclear diatomic. So it has no net dipole. And taking those 2 atoms and making the bond vibrate more or less and changing the average bond length doesn't change the fact that it has no net dipole. So nitrogen gas is not IR active, which as it turns out is a good thing. Similarly, oxygen gas, being a homonuclear diatomic, is also not IR active. Carbon dioxide is. Yes, it is a nonpolar molecule. If I draw the Lewis diagram for carbon dioxide, it looks like that. And if I were to have a vibrational mode in which the oxygen stretched out more and then stretched in more, so I was to kind of go back and forth between those 2 extremes, that is not IR active because we go from no net dipole to no net dipole. But if, and boy do I wish you could see my hands moving around like a crazy thing right now, if I were to take my carbon dioxide molecule and stretch over to one side, like so, and then stretch way over to the other side, like so, and imagine vibration between those two extremes, that asymmetric stretch where the one oxygen's getting farther, then it comes in, and the other oxygen gets farther, and then it comes in, and so on and so forth. That stretch is IR active. It is changing the net dipole of our molecule. So carbon dioxide is IR active. Turns out that's also pretty important. Water is also IR active. It's a polar molecule. You can certainly imagine that many different stretches would change the average bond lengths, change the direction in which that dipole was pointing. And so water vapor is also IR active. Now I mentioned here that these are the 5 most prevalent gases in our atmosphere. Nitrogen's the most common, then oxygen. Argon's ahead of carbon dioxide. Where water fits into that scheme depends on how humid it is where you happen to be. So why did I pick atmospheric gases for this question? Well, because while infrared spectroscopy is great for analyzing molecules in a lab and looking at their functional groups and all sorts of fun academic questions like that, it's also got a massively important global consequence. And that is the fact that gases that absorb infrared radiation are what we call greenhouse gases. And I can't imagine there's a person in this class that has never heard the term greenhouse gas before. But the actual definition of a greenhouse gas is one that is capable of absorbing infrared radiation. Now, greenhouse gases in and of themselves are actually really important to the planet's climate. If we didn't have any greenhouse gases at all, Earth would be bloody cold. So they play a role in moderating the Earth's temperature, in keeping some heat on the planet. We wouldn't be 0 Kelvin or anything like that, but we'd be a lot colder. But if you change the levels of any particular greenhouse gas, you're going to have an impact on the climate. If we were to all of a sudden come up with some technology that sucked all the greenhouse gases out of our atmosphere, it'd get really cold. If we doubled the level of greenhouse gases, it would get really hot. This is not a homogeneous effect. It varies from part of the world to other part of the world as different things vary, like humidity levels, but also temperature is an important thing. It's sort of weird that the temperature is determined by the temperature, but to some degree it is. The position on the planet relative to the angle from the sun, all these things matter. So how do greenhouse gases do their job? Before we start commenting on rising levels or anything else, let's just use a baseline. What do greenhouse gases do? Well, we have to think about how the planet gets heat. And of course, the planet gets the majority of its energy coming from the sun. Light from the sun comes to Earth. Most of the energy that gets through the atmosphere is in the form of visible light. The stuff that gets down then, some of it just bounces right back and flies right back through the atmosphere, right out into space. That's about 1/3 of it. The other 2/3 is absorbed by the Earth. Now, the Earth doesn't re-emit it as visible light. The Earth re-emits that energy in the infrared spectrum. You hear this term black body radiation because you can't see it. It's invisible. And that infrared radiation, if it travels through the atmosphere, back out through the atmosphere without ever hitting a molecule that can absorb it, just passes right back out into space. It has no impact on the planet's temperature whatsoever. So if you were very, very, very high altitude and had very low CO2 levels up there, then much of that would be emitted back out. Part of why it's cold up there. On the other hand, if you're at lower altitude and that infrared radiation being emitted by the planet, that black body radiation, hits some sort of greenhouse gas, and it doesn't have to be carbon dioxide. It could be the water vapor, it could be methane, it could be any number of other things. Then, well, the greenhouse gas is a greenhouse gas because it absorbs infrared radiation, so it gets absorbed by the greenhouse gas. And then we have higher energy gas particles flying around. Now, initially, it's a vibrational energy level increase, but gas particles are constantly flying around and smashing into each other. And when they do that, there's a transfer of energy, and that increased vibrational energy can be converted into translational energy or kinetic energy. So the gas particles fly around faster. Well, when gas particles fly around faster, when you raise their average kinetic energy, you are raising the temperature. That's actually what temperature of a gas is. It's a measure of its kinetic energy. And so, long story short, infrared radiation from the planet hits greenhouse gas, increases temperature. And this lovely schematic here that I borrowed from Professor Russell's notes shows us exactly what that's doing. We can see incoming solar radiation here. So light energy coming in from the sun. Some of it just bounces off. That was about the third. Some of it manages to pass through the atmosphere without ever hitting any greenhouse gas. That's okay. And then over here, we have what they are referring to as the greenhouse photons, the photons of energy that got trapped by being absorbed by some sort of greenhouse gas. And they are the ones that are raising the temperature. I've also included links to a couple of visualizations from the King's Center for Visualization in Science. These are really cool little interactive apps or tools, whatever you want to call them. You can use them on a computer, you can use them on a phone. And the first one talks about infrared radiation and greenhouse gases and climate, and lets you play around with that a bit. And the second one is an app that allows you to essentially overlay different IR spectra for different greenhouse gases so that you can see how they interact with the black body radiation emitted from the Earth. Because at the end of the day, we are more worried about greenhouse gases that absorb the radiation of the wavelengths that the Earth emits than we would be about ones that absorbed other wavelengths that the Earth isn't emitting very much of. But we're also, of course, concerned about greenhouse gases whose concentrations are changing in a significant way. And if anybody tells you otherwise, they're full of it. Atmospheric carbon dioxide levels are changing, point blank. They've increased by about 30% over the last 60 years. That's not negotiable. That's a measured scientific fact. They're also rising about 4 times faster now than they were 60 years ago. Now, we are certainly developing technology to mitigate this. I am not saying that we cannot develop technology to mitigate this. I am saying we must prioritize the development of technology to mitigate this. Because it's not just about CO2. When you raise the average temperature, you increase the humidity. By definition, more water molecules evaporate, and you start melting ice as well. And water is also a greenhouse gas, as you've seen. So we do need to worry about that as well. And methane is actually a more powerful greenhouse gas than carbon dioxide. It hasn't made it into the news as much, other than people who like to joke about farting cows, which is really a distraction. But the wavelengths which it absorbs are very, very important. And if we actually start melting permafrost because rising levels of other greenhouse gases have raised the temperature enough to do that, then we've got to start worrying about methane emissions as well. And so infrared spectroscopy, really useful experimental technique. Infrared radiation has consequences vastly beyond the scope of this course.